Lesson is on properties of materials. We will first look at the elastic properties of materials. What is the meaning of elasticity? Well, we are all familiar with it. If we say this is an elastic band, why do we call this an elastic band? Because it is elastic. Now, what is that particular property called elasticity? I think it is very often misunderstood by many people, the property called elasticity. Let me ask you, is this elastic band or this aluminum rod, which is more elastic? What do you think? This is aluminum. Well, this is the elastic band. Which is more elastic? Well, I need to rephrase that question to make the meaning of elasticity clearer. Which of these can withstand a greater deforming force and still keep its shape? Now, you know that if I use a greater deforming force on this elastic band, it's going to stretch beyond the limit so that it will not return to its original shape. Whereas, if you look at this ball, I can apply a large amount of deforming force on it. It still will not change its shape or its size considerably. Well, it will change momentarily, but it will regain its shape when the deforming force is removed. Why is steel used for constructing bridges? You see, bridges and great buildings are made to withstand great stresses, great deforming forces. Under the action of great deforming forces, if a structure begins to lose its shape, then the structure will collapse. And therefore, materials used for constructing bridges and tall buildings must be very elastic. Now, does it mean that they should be like this? No. It means under the action of great deforming forces, they should be able to keep their shape. They should be able to withstand the deforming force. So elasticity is the property of an object to withstand deforming forces. You must understand elasticity in that sense. Therefore, we will define elasticity like this. Elasticity is the ability of an object to regain its original shape after being deformed by an external force. Alright, steel is much more elastic than rubber because steel can withstand large amount of deforming forces but still keep its shape. Deformation is caused by a stress. What is the meaning of stress? Stress, deforming force per unit area. Force per unit area is called stress. If I can apply a certain amount of force on a certain surface, what is the force per unit area? And that is a measure of stress. So stress can be defined as force divided by area. Force per unit area. What is the unit for measuring stress? Force is measured in Newton, area in meter squared. Therefore, stress is measured in Newton per square meter. Now, a stress that produces a change in length is called a tensile stress. Well, I will talk about each of those. On the other hand, a stress that produces a change in volume is called a compressional stress. And there is one other stress, that is a stress that simply deforms the object at a certain angle is called the shear stress. So there are three types of stresses that we will be looking at. The first type of stress is tensile stress, a stress that will change the length of the object. Compressional strength, a stress that changes the volume of the object. And shear stress that will change the angle. Let me see if I can show these different stresses using a simple example. Now here I have a lead ball hung from a string. That means the weight of the lead ball is pulling the string, causing its length to change. Is that right? It's causing an elongation. So you have a tensile stress. The stress caused by the weight of this object is a tensile stress. Now let me ask you, how will I measure this stress? Stress is force per unit area. Now, what is the area on which this force is acting, the weight of this object? The area on which this force is acting is the area of cross-section of this string. For example, if this is the string which is being pulled, it is being pulled at this area. It is the area of cross-section. If the wire is circular, it's a round object, then that cross-sectional area is a circle. And therefore, if I can now pull this by suspending a weight, that weight will be acting at this cross-sectional area. Area of that circle is pi r squared. Now, watch this one, a similar example. I have a wire being stretched by a load. You can see this load stretches the wire, causing an increase in length. This is a tensile stress. Now, in many construction industries, tensile strength that causes increase in length or decrease in length. For example, if I keep, let me see if I can show this completely. If I keep this on the book and load it up at the top, you can see the stress is now changing its length, decreasing its length. Is that right? This is a tensile stress. So any stress that causes a change in length is a tensile stress. Now look at this stress. I have a ball that is held between the clamps here, and if I tighten the clamp, now look at this, I'm going to tighten it. What am I doing? I'm applying a force, pressing the object from either side. It is a compressional stress. Now, the third type of stress I talked about. Do you remember the third type of stress I talked about? It's called the shear stress. Shear stress. Let me see if I can show that to you. You can see I have a book here. If I apply a tangential force on the top surface, look what happens to the book. Now, what happened here? There is a change in the angle before I apply the force. Now, this is before I apply the force. Before I apply the force, the edge of the book is vertical. This angle is 90 degrees. Now what happens when I apply a shear force? The force I'm applying is tangential to the top surface. Now what happens? The edge of the book is now at an angle. So this is the effect of a shear stress. A shear stress causes deformation at an angle. If you look at this edge, wasn't that vertical before the force is applied? And now, after the force is applied, look at that edge. It now makes an angle with the vertical. So, we got three types of stress. What are they? Tensile stress, compressional stress, and shear stress. Here I have illustrated the three types of stresses. A stress that causes a tension, a stretching force, which changes the length, either increase or decrease. Well, that is a tensile stress. You have a compressional stress, and look at this, a shearing stress. The forces are parallel, and what will happen as a result of this force? As a result of this force, the object is going to look something like this a little later, like this. So you have a change in the angle, that is a shear stress. Well, now the question is, if you have a stress acting on an object, what will that stress do? A stress will produce a strain on the object. When an object is subjected to a stress, it will suffer a strain. Well, the ratio of the change in length to the original length is called the tensile strain. So when I suspend this ball from the string, the string is subjected to a stress. As a result of the stress, the length of the string will increase slightly. If you now take the ratio of that increase in length to the original length, that ratio is called the tensile strain. So if delta L is the increase in length for an original length L, then tensile strain will be delta L over L. Now tell me, what is the unit of tensile strain? Delta L is measured in meters, L is measured in meters. It has no unit. So it is a simple ratio and it has no unit. The ratio of the change in volume delta V to the original volume V is called the bulk strain. Bulk strain. You see, the compressional forces produce a bulk strain, change in volume. And in most cases, because compression causes a decrease in volume, we normally take this delta V as negative. Why delta V is negative? Because the compressional forces generally cause a decrease in volume. So look at this. Bulk strain is negative delta V divided by V. All right. Let's now talk about Young's modulus. What is Young's modulus? For an object that is subjected to a tensile stress, there will be a tensile strain. Is that right? If you now take the ratio of the tensile strain, the tensile stress to the tensile strain, that ratio is called the Young's modulus of that material. So the ratio of tensile stress to tensile strain is called the Young's modulus of elasticity. It's the modulus of elasticity. So what is the definition of Young's modulus? Young's modulus is the ratio of tensile stress to tensile strain. You can see if you have a big column in here, and if you apply force F on it, that will cause a decrease in length, a change in length to delta L. That delta L divided by the original length will be the tensile strain. And what is the tensile stress? Tensile stress is this force F is applied on this area A, so the tensile stress will be that force divided by that area. So stress is force divided by the area. The strain is delta L divided by L, and Young's modulus is the ratio of stress to strain. In other words, stress divided by strain is a measure of the Young's modulus of the material of this. Now, we represent the Young's modulus by the letter Y. If Y is the Young's modulus, what is the equation for it? It is tensile stress divided by tensile strain. And in this case, the tensile stress is F divided by A. A is the area which I am now pointing. That is the area on which the force is acting. So the stress is that force divided by that area, and the strain is delta L divided by the original length. So I can write it as F over A divided by delta L over L, and that is the Young's modulus of elasticity. What is the unit for measuring Young's modulus? You know that the unit for stress is Newton per meter square. Unit for strain has no unit. It is a ratio of two similar quantities. Therefore, the unit of Young's modulus is Newton per meter square. Let's solve this equation for delta L. Can you do that? You have a Y equal to, let me write that over here. Young's modulus Y equal to F over A divided by delta L divided by L. Now, this is stress divided by strain, and that will be F times L over A times delta L. Is that right? F over A divided by delta L over L. This L will go up. F times L over A times delta L. Can you solve for delta L from here? Well, delta L, if you cross multiply, Y times A delta L equal to F times L. So delta L will be F times L divided by AY. Is that right? Okay, let's write that down. So delta L is F times L over A times 1 over Y. That is the change in length under this stress. So the increase in length of a rod or wire under tensile stress is inversely proportional to the Young's modulus of the material. That means greater the Young's modulus, less will be the deformation. So if you want to use a material for hard construction, you need a material of very large Y value, a very large Young's modulus, so that under the action of great stress, the deformation will be very, very small. Okay, let's now talk about bulk modulus. Bulk modulus. Well, I think it follows from our discussions. Bulk modulus is the elastic modulus that talks about the change in volume. The ratio of the volume stress or the bulk stress to the volume strain is called the bulk modulus. Now we normally represent the bulk modulus by the letter B. So B equal to volume stress divided by volume strain. And volume stress is, of course, F divided by A. And volume strain is the change in volume divided by the original volume. And can you solve for delta V from here? Well, again you can see B is measured in Newton per meter square, which is the same as the unit for measuring stress. Well, The reciprocal of the bulk modulus, the quantity 1 over B, is called the compressibility of the material. How easy is an object, how easily can you compress an object? The value, the compressibility of a material tells you how easily it can be compressed. And that is the reciprocal of the bulk modulus. What does that mean? It means greater the bulk modulus, greater will be the difficulty to compress it. In other words, 1 over B, when B is very large, 1 over B is very small, the compressibility will be very small. For an object of very large bulk modulus, the compressibility will be very small. It will be very difficult to compress it. So 1 over B is called the compressibility of the material, and we represent it by the lowercase k. K equal to 1 over B. Let's now talk about the shear modulus. Shear modulus. Now we talked about the shear stress. Shear stress is caused by parallel forces which changes the shape of the object at an angle. And what is the shear strain? Well, let's talk about that. The shear stress is produced when a force is applied tangentially to the surface, like this. You have the original surface, apply a force tangential to that. This is a shear force, and this creates a shear stress. Tell me, if this force is acting on this area A, what is the shear stress? The shear stress is F over A. Now what is the shear strain? You notice that the strain in this case is actually measured in terms of the angular deformation. The deformation here is measured in terms of the angle. Therefore, the shear strain is the tangent of the angle of deformation. So here the change in shape produced by the stress does not involve in a change in volume or change in length, but involves in a relative displacement of two surfaces of the body. You see, the lower surface has not moved, but the upper surface has been displaced. A relative displacement has occurred for the two surfaces. That means the deformation is actually an angle. The shear strain is given by the tangent of the angle of deformation. Now, this angle is the angle of deformation, and that will be, therefore, the tangent of that angle will be the shear strain. Now, if this is the angle here, tell me what is the tangent? If the upper surface has been displaced by a quantity delta L, that means this length is delta L, and the height of the object is h, has the height changed? No, the height hasn't changed. So if the upper surface has been displaced by a small distance delta L, then the tangent of the angle of deformation will be that opposite side divided by the adjacent side. Delta L divided by h is the shear strain here. So shear strain is tangent of the angle of deformation, which is delta L divided by h. Okay. We represent the shear stress by S. S represents the shear modulus of the material, not the shear stress, shear modulus. So shear modulus equal to shear stress divided by the shear strain. And what is the shear stress in this case? It will be F divided by A, and the shear strain is the tangent of the angle of deformation, which is delta L divided by H. So that will be S, the shear modulus, is F over A divided by delta L divided by H. Now, shear modulus may also be a torsional type, resulting in the twisting action. A torsional type. Now, what is that? What is a torsional type of deformation? Let me see if I can show the torsional type. Now, if this mass is hanging from this wire, look at what happens when I twist this mass. When I twist this mass, what it does is it is turning this wire. It is turning this wire. In other words, this shear modulus is kind of torsional modulus. You see, the change in angle is actually producing a change in angle, twisting of the wire. Now, it is fixed where I'm holding. That means the wire is now being twisted, or the shear strain is the angle of twist. So, the shear modulus may also be a torsional type, resulting in the twisting action of a torque. Now, you understand what that means. All right. I have now got a table of values that shows the standard values of the Young's modulus Y, the bulk modulus B, and the shear modulus F of some common materials. If you are a civil engineer building bridges and constructing big buildings and so on, you should be familiar with these properties of the materials. Is that right? Now, here is the table of values. We got the material aluminum. The Young's modulus is 7 times 10 to the 10 Newton per meter squared. Its shear modulus is 2.4 times 10 to the 10 Newton per meter squared, and its bulk modulus is 7 times 10 to the 10 Newton per meter squared. You can see the modulus of elasticity, all three types, are measured in Newton per meter squared, which is the unit of stress. The unit of strain, strain has no unit. Well, if you look at steel, Young's modulus is 20 times 10 to the power of 10. It is very highly elastic. The shear modulus is 8.1 times 10 to the 10, and the bulk modulus is 16 times 10 to the 10. Tungsten has the highest elastic modulus values, and that means tungsten is very highly elastic. It can withstand very large deforming forces without permanently being deformed. Well, let's do a small problem. A 100 kilogram mass is suspended using a cable with a diameter of 2 centimeters. What is the stress in the cable? I showed this to you earlier. The stress is actually caused by the weight of the object hanging from it. And what is the area on which that weight is acting? It is the cross-sectional area of the cable. And the cross-sectional area of a cable like this is a circle. Alright, so here's the cable, and here is the 100 kilogram mass hanging from it. What is the force pulling the wire? It is the mass of this multiplied by G, 100 kilogram times 9.8 meter per second squared. That will be 980 Newton. So this cable is now being pulled by a force of 980 Newton. And this force is distributed on what area? It is distributed over the cross-sectional area of the wire. The radius of the wire, we are given the diameter. If the diameter is 1 centimeter, the radius will be, if the diameter is 2 centimeter, the radius will be 1 centimeter, that is 0.01 meter. What is the area of cross-section? The cross-section is a circle of radius 0.01 meter. Therefore, the area of cross-section is pi r squared. That is pi times 0.01 squared. And we can write it as 3.14 times 10 to the negative 4 meter squared. So a force of 900 Newton is acting on an area of 3.14 times 10 to the negative 4 meter squared. What is stress? Stress is force per unit area, and that will be the amount of force divided by the area on which that force is acting. Therefore, the stress is 3.12 times 10 to the power 6 Newton per meter squared. Okay, let's do another problem. A metal wire 1 millimeter in diameter and 2 meter long hangs vertically with a 6 kilogram mass suspended from it. If the wire stretches 1.4 millimeter under tension, what is the value of Young's modulus for the metal? Well, to find the Young's modulus, first we need to calculate the stress, force divided by area. Then we have to calculate the strain. What is the definition of strain? The ratio of the change in length to original length. Delta L, this is delta L, 1.4 millimeter. And we know the original length. So we can calculate the strain from these values, and stress we can calculate the same way we did it in the previous problem. The radius of the wire we need to calculate from here. What is the diameter? The diameter is 1 millimeter. The radius is 0.5 millimeter. Convert that to meters. It is 5 times 10 to the negative 4 meter. Therefore, the area of cross-section on which the force is acting is pi r squared. Pi times 5 times 10 to the negative 4 squared, and that is 7.9 times 10 to the negative 7 square meter. And what is the force? The force acting on that wire is the weight of this 6 kilogram, which is 6 kilogram times 9.8 meter per second squared. That is 58.8 Newton. Therefore, what is stress? Stress is force divided by the area. A force of 58.8 Newton is acting on an area 7.9 times 10 to the negative 7 meter squared. So divide the force by that area, because stress is 7.4 times 10 to the 7 Newton per square meter. Alright, we now got the stress. We now need to obtain the strain. The original length is 2 meter. The increase in length is 1.4 millimeter. Convert that to meters. 1.4 times 10 to the negative 3 meter. Therefore, the strain is delta L divided by L. That is 1.4 times 10 to the negative 3 divided by 2. That is 7 times 10 to the negative 4. Well, we got the stress, we got the strain. Therefore, Young's modulus is stress divided by the strain. and that is 7.4 times 10 to the 7 Newton per meter squared divided by 7 times 10 to the negative 4, and that is 1.1 times 10 to the 11 Newton per meter squared, and that is the Young's modulus of this metal wire. Can you quickly look back on the table that I provided and tell me what metal is this wire which has this Young's modulus? Does it agree with the value for steel? I think this is steel. Alright, let me know if you got the value for the answer for that. What metal is this wire made of? Okay, another problem. A rectangular steel column 20 centimeter by 15 centimeter supports a load of 12 metric tons. A metric ton is 1,000 kilograms. If the column was 4 meter length before being stressed, what is the loaded length? Well, what we have is a column that is being compressed by, well, it's a tensile stress, but under the action of the tensile stress, the column decreases its length. That is the situation we have. Now, the Young's modulus for steel, well, the Young's modulus for steel is 2 times 10 to the 11 Newton per meter squared. We will need that in this calculation. And this is the column which is before it gets deformed. Now, it's a 20 centimeter by 15 centimeter, means if you go to the top of that column and measure the length and width, it is 20 centimeter by 15 centimeter, and you can calculate the area of the top of the column. The force, the deforming force, is going to act on that area. Alright, therefore the area is 20 centimeter, 0.2 meter times 0.15 meter, that is 0.03 meter squared, and that is this area. This area is 0.03 meter squared, and on that area is now a load of 12 metric tons. This is the load of 12 metric tons, and that means the weight of this 12 metric tons is acting vertically on this column. What is that weight? The mass is 12 times 1,000 kilograms. Multiply that by 9.8. You get 1.2 times 10 to the power of 5 Newton. And that is the force that is acting on that column. The total force acting on the column is 1.2 times 10 to the power of 5 Newton. And what is the area on which this force is acting? It's 2 times 10, the area is 0.03 square meter. So this amount of force is acting on this much area. What is the stress? Stress is force divided by area, and this amount of force, 1.2 times 10 to the 5, is acting on the area 0.03 meter squared. Therefore the stress is 4 times 10 to the 6. Well, in this problem we have now obtained the value of stress. We know the Young's modulus, and we know the original length of the column. The original length is 4 meter. What are you supposed to find? We need to find the loaded length. In other words, when the load is sitting on it, its length is decreased slightly. You need to find that loaded length. In order to find the loaded length, you need to find the change in length delta L. So that's what we're going to do now. We have the original length L equal to 4 meter. Therefore, the strain is delta L divided by L. And we need to find delta L in order to find its loaded length. So, strain therefore is delta L divided by 4. Stress is 4 times 10 to the 6. Strain is delta L divided by 4. The Young's modulus is 2 times 10 to the 11. What is the equation for Young's modulus? Y equal to stress divided by strain. That means Y is 2 times 10 to the 11. 2 times 10 to the 11 is 4 times 10 to the 6 Newton per meter squared divided by delta L divided by 4. Y equal to stress divided by strain. You can see the only unknown here is delta L, the change in length. Can you solve for delta L from here? First of all, this 4 is going to go to the top. Therefore, this delta L will be 4 times 10 to the 6 divided by this number. I hope you understand how this is done. So, delta L is this quantity multiplied by this 4 will go to the numerator, and this quantity will be on the denominator. And that is 8 times 10 to the negative 5 meter. Well, this is the change in length. This is the original length 4 meter. Therefore, what is the loaded length? The loaded length is L minus delta L. So, loaded length is L minus delta L, 4 minus 8 times 10 to the negative 5, and that is 3.99992 meter. You can see the change in length is so very small. In many cases it is very undetectable, and that is very important if you want to construct the columns of a bridge, and those are supposed to withstand great stresses. It must be constructed with materials that have large elastic modulus, so that the loaded length will not be very different from the actual length. What happens if the loaded length is much different from the actual length? Well, it means the change in length will be considerably large. That means the weight of the bridge will create cracks on the columns, which will eventually destroy the bridge. Well, if you remember a bridge collapsing in one of the Midwestern states, you remember that one? That was a construction fault. In fact, the architects did not actually use the right kind of materials for the construction of the bridge. So if you are going to be a civil engineer, you know that these are crucial decisions that you need to make when you design a bridge or a big skyscraper and so on. Another one. A shear force of 750 Newton is applied to one face of aluminum measuring 10 centimeter on a side. This is an aluminum block, and on the upper surface we apply a force of 750 Newton. And what is the area on which that force is applied? The surface of the aluminum is 10 centimeter, it's a cube actually, 10 centimeter on a side. That means the top surface area will be 10 centimeter multiplied by 10 centimeter, 0.1 meter times 0.1 meter. So the 750 Newton is acting on an area 0.1 meter times 0.1 meter. We can now calculate the stress. and the strain will be the tangent of the angle of deformation. If the top surface is displaced, this is called the displacement of the top surface, by a distance x, then tangent of angle phi will be x divided by 10. Isn't 10 the height? This is a cube of length 10 centimeter, width 10 centimeter, and height 10 centimeter. So if x is the displacement and 10 the height of the block, then tangent of angle phi is x divided by 10. We can leave this unit in centimeters so that x will also be in centimeters. Alright, we need to find what is the displacement relative to the opposite phase. Now this is the phase resting on the floor, and the top face got displaced. We need to find that displacement x. Okay, 750 Newton is applied on an area 0.1 meter times 0.1 meter, that is 0.01 meter squared. Therefore, stress is force divided by area, that is 750 Newton divided by 0.01 meter squared is 7.5 times 10 to the 4 Newton per meter squared. You got the stress. What is the strain? Strain is tangent of the angle of deformation. Shear strain is tangent of angle phi. And what is tangent of angle phi? Opposite side divided by the adjacent side, x divided by 0.1. Well, this is aluminum, and what is the shear modulus of aluminum? Can you look back on the table and get the value of the shear modulus of aluminum? You have S equal to 2.4 times 10 to the 10 Newton per meter squared. So, we know the shear modulus for aluminum, we know the stress, and we know the strain where we need to find this x. So, we can now say the shear modulus equal to shear stress divided by shear strain. There you are. That means 2.4 times 10 to the 10 equal to stress is 7.5 times 10 to the 4 divided by strain is x over 0.1. Okay, can you give me what x equal to in this case? If you understood the way we solved for delta L in the previous problem, you can tell me how to solve for x here. You can see this 0.1 will go up. And if you want to solve for x, this x can be taken to the left and this quantity can be brought to the denominator. So my numerator will be 7.5 times 10 to the 4 times 0.1, and the denominator will be 2.4 times 10 to the 10. So x equal to 7.5 times 10 to the 4 Newton per meter squared multiplied by 0.1 divided by 2.4 times 10 to the 10. And that will be 3.13 times 10 to the negative 7 meter. And that will be the displacement of the top face of the aluminum cube when this force is applied. I will now stop this part of the lesson here, and I will give you a second part of the lesson where we mostly discuss the concept of pressure. Alright, I will get back to you with that lesson shortly.